All right, let's go through these. So when the directions ever say evaluate, that just means figure out what this log is equivalent to. We know that logs equal exponents. So another way to think of it is what would that exponent be for this logarithm? And to help visualize that, we can simply rewrite these in exponential form. So we can see, well, what is that missing exponent that I'm looking for? The first one, when we write that in exponential form, again, set these equal to x, because that just helps you kind of think about what we're solving for. I'm solving for this exponent, this unknown value, so we'll just call it x. And when you rewrite it in exponential form, you start with the base. But in this case, there is no base. There's no subscript there. That means this is the common logarithm, and the base of a common log is always 10. So we'd write that as 10 to the, and we don't know what the exponent is, right? Because the log equals an exponent. We don't know. We're trying to figure out what is that exponent to make this true. So 10 to some exponent equals 100,000. And so then the way we can solve this, you might be able to just to look at that one and see, oh, I know what my exponent's going to be. But if you use the properties that I showed you on Wednesday, where to solve an exponential equation like this, you can just get a common base from both sides, the left side and the right side. And so if you think about it, obviously those two numbers are going to have the same base of 10. And so I can just rewrite that left side as 10 to the, count the zeros, there are 5 of them. And so I just rewrote the right side as 10 to the 5th. And now we've got the same base on both sides. And so you just set those exponents equal to each other. Say, okay, so x has to equal 5. And there's no other calculations. We're done, right? We know, okay, got my answer. X is 5. For this next one, let's set it equal to some variable. You can use x again. That's fine. And I'm going to rewrite this in exponential form. So we start with the base, which is in the basement, the 3. Raise it to the exponent. That's our unknown. I don't know what the exponent's supposed to be, so I just put in a variable there in its place. And it's going to equal this 243. You might not know off the top of your head 3 to some power to get 243, but if you keep multiplying it enough, we'll figure out that y has to equal 35 or 5? Well, that's an exponent. Like 3 raised to the 36th power would be gigantic. Because, like, here, Gavin, ready? Oh, yeah, I looked at it. 3 times 3, it's 9, 27, 81, and then 243. Yeah. Do you see it now? Yeah. Okay, cool. Hey, I math wrong all the time. All right, this last one is the one you had to think a little bit more, and that's where the writing them in the same base is actually really helpful. Because let's say this equals z. We'd write 8 to some exponent equals 32. And I don't know e to some exponent equaling 32. I don't know what that is off the top of my head. Because 8 to the first power is just 8, but 8 to the second power is 64. And this is less than that. So it's going to be something in between 1 and 2, meaning we're going to have a fraction. And so the way to help with these problems is look at the 8 and the 32 and think, what's the common base between the two of them? What number that's smaller than those numbers could I write them as some power of? And I happen to know that 8 and 32 are both powers of 2. So I'm going to rewrite both sides as 2 to some exponent. Now on the left side, this 8, that's the same as 2 to the 3rd. But remember, it still has this z exponent, or x, whatever. It still has that unknown exponent. On the right side, 32 is 2 to the 5th. On the left, when you have an exponent raised to another exponent, you just multiply them together. So I can actually just say, oh, this is 2 to the 3z, or 3x, equals 2 to the 5th. And so now finally at this point, I've got the same base written only one time on the left side and on the right side. So if the bases are the same, we know the exponents also must be equal. So I can just say, okay, so 3 times this variable has to equal 5. Solve that for the unknown, just divide both sides by 3. So your answer for this one should be 5/3. Anyone get 5/3 for that last one? A little tricky. Any questions on any of these? Is this familiar from Wednesday a little bit? Remember doing that? So these types of equations we would call your basic exponential equations. We can solve for an unknown exponent without having to use logarithms. But oftentimes in the real world, we're going to get problems that aren't that simple, aren't that nice. And so today we're going to look at finally solving what I'm calling advanced exponential equations. Basically, these are going to be equations where you're not going to be able to figure out what the exponent is just by like rewriting it or looking at it. We're going to have to use the logarithm. We're going to have to use our calculator, and we're going to have to figure this out together. So whenever you can't get a common base, we're going to use logarithms. We're going to rewrite it in log form and then just use the calculator. So don't worry about writing all these words, I guess. Write the title and then write this little demonstration problem on the bottom. 10 to the x plus 8 equals 1,000. And once you got that written down, go ahead and grab out your calculator. So we'll be using the calculator all day today. So this first one is pretty straightforward. We actually could write this with the common base like we've been doing and solve it that way, but I want to use it to demonstrate how we would solve it with the logarithm, because I said we can use logarithms to solve every problem. We don't have to find that common base for those ones that we just did in the warm-up. We could have used our calculators and logarithms to solve them, but sometimes it's nicer, easier to do it if you just kind of visualize it that way. So I'm going to use this one and show you how we could actually use it with the log. First, make sure that your exponential equation only has the 3 parts: a base, an exponent, and an answer. If there were like something else in front of the 10, like being added or whatever, you'd want to subtract it off. Or if it was multiplying, you'd want to divide that off. You want to make sure that there are only those 3 parts: a base, an exponent, equals an answer. Once you have it like that, then we can go ahead and rewrite it in log form. So we start by writing the word log. Then the base goes into the basement. The base for this problem would be 10 because that's what's holding up the exponent. So log base 10 of the answer of 1,000, and logs equal exponents, and our exponent here is x plus 8. So we were able to bring that exponent or the variable out of that exponent position and down to the regular calculating line. Now from this point, if I want to get the x by itself, what would I have to do to both sides? Yeah, right, that's x plus 8. We'd want to subtract an 8. Now, would I subtract the 8 from the 1,000? Or would I subtract the 8 kind of like after the parentheses, after the logarithm? What do you think? So we're going to do it after the logarithm, because like log base 10 of 1,000, that's one thing, one variable, one number. All right. I'm going to calculate that first, and then you would subtract the 8 afterwards. Because I'm not taking the log of the 8 or the negative 8. Oh, and by the way, log base 10. Do I need to write that subscript of a 10? No, right? That's a common base. So we can just simply write this. I'll go over here. Log of 1,000 parentheses, because that's base 10. And then if I'm subtracting 8 here, subtracting 8 there, those cancel out. So I'm going to write minus 8. Very important to make sure that that minus 8 is after the closed parenthesis. You're going to close that parenthesis first for the logarithm, and that would equal x. Go ahead and type this into your calculator, because you've got the common log button on your calculator that doesn't have a subscript. That means it's the log base 10. So go ahead and type log 1000, close the parentheses, and then subtract 8. I want everyone to make sure you can use the log button correctly. Should get a nice number. Yep. Is it working for everybody? So for this one, I think you need to type in the number in the parentheses first. So try typing 1000 and then press log and then subtract 8. There you go. That's the answer. That work for you too? Yes, you got it. Anyone over here having, you got it? You able to type it in? You good? Nice. Yes? You good? All right. So you can type log 1000 minus 8. So that x equals -5. Dun 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 dun. You use your calculator to solve. Good job. And we could have written this as a common base, right? 1000 is just 10 to the third. X plus 8 equals 3. Set those equals, subtract 8. 3 minus 8 is -5. So we could have done that the common base way also. But it works with logs, and that's where we're going today. All right, let's see if you can solve this one. 2e to the x equals 26. Why don't you grab it out? Remember that before you write it in exponential form or into log form, make sure that you only have a base, an exponent, and an answer. You can't go right to the calculator right off the bat or right to log form. There's one thing we have to change or take care of in this equation before you rewrite it in log form. And then remember, when you take a log with a base of e, we have a button for that too. That's the natural log. So look in front of the base e. Like this exponent is only on the e. So how do you get rid of that 2 first? Yeah, because like the exponent is only on the e. That 2 isn't part of that equation. You have to get rid of that 2 first. Then you can go ahead and rewrite it. Cool. Nice job. So just like this one, we have to have a base, an exponent equals an answer. You have this base, exponent, answer, but there's also this extra 2 in front. Yeah. Yeah. Good job. So you've got the base, the exponent, and the answer. Rewrite it in log form. Nice job. Yeah. Yeah, and log base e is just ln, natural log. All right, so the important thing here is to recognize that the 2 and the e to the x are 2 separate bases. And when I rewrite it in exponential form, I can only have one base raised to an exponent, meaning we've got to get rid of that 2 first. What operation should I do to get rid of that 2, to cancel it out? Divide. Let's do division, right? I'm going to divide by 2 on both sides so that those are gone. And now I do just have a single base. E to the x equals 13. Now I've got one base to the exponent equals the answer. So I want to solve for that unknown exponent. We're going to rewrite it in log form. So that'd be log, the base goes in the basement, of the answer equals x. But log base e is special. It's also a very popular logarithm that's used. And so we actually have a separate button for that. That's called the natural log, which is just ln. So I'm going to take the ln of 13, and that equals x. So once you've got it to that point, well, we can just take your calculator out, and there's an ln button. You press ln 13, close the parentheses, and that's literally our calculation. About 2.6. Everyone got something like that? Yeah, if you rounded. So x is approximately 2.6. Right, now that's one where we definitely need the calculator. In our head, we couldn't think e to some power being 13. It's an irrational number. We're going to get an irrational answer. So those first two we did, that was nice because it was a log base 10 and a log base e. We have a button for each of those in our calculator because they happen most frequently. What about when the base is not a 10 or an e, though? We have to do a little bit of work. So like this situation, if we were to rewrite it in log form, you don't need to put this part down, but if we did, we'd get log base 2 of 12. And that's what I need to type into my calculator. But that's a problem because you don't have a log base 2 button on your calculator, right? And the calculator couldn't fit a button for every possible base. There's an infinite combination. Your calculator would be, bigger than the world. So how do you do this? Because we can't type this in. So instead, we're going to take advantage of one of our properties of logarithms. So when we're solving an equation to get x by itself, we cancel out one term on one side. And don't you always do that same operation on the other side to keep the equation balanced? Right? Like if I add 5 to the left, I add 5 to the right. We're allowed to do that, right? That's a valid mathematical procedure. Well, it turns out that applying a logarithm or taking the log of each side is also an operation, right? I told you that log is a new operation for solving for unknown exponents. So I can actually take the log of the left side, and if I do that, I'd also have to take the log of the right side to keep the equation balanced. We're allowed to do that because taking a logarithm is just another math operation, kind of like squaring or square rooting. So our equation is just going to become log of 2 to the x equals log of 12. So I simply took a log of both sides. Now, the one thing you have to be consistent of when I take the log of both sides is make sure that both of those logs that you're bringing into the problem have the same base. I could use any base. I could do log base 6 of the left and log base 6 of the right if I wanted. But here I'm choosing to use log base 10 because I've got a button for that on my calculator, right? That's the common log. Now that I've written it this way, log of 2 to the x, is there something I can do that we know with logarithms to help me with that exponent? Think about our log properties. We had a product property, a quotient property, and there was a power property. There's something we can do when you're taking the log of something and there's an exponent. What can I do with that exponent on a logarithm? we could take that exponent and move it in front of the log, making it a coefficient. Does anybody remember that rule that we did earlier? Yeah, that was on Tuesday. So I'm going to rewrite this again as x times the log of 2 equals the log of 12. So by applying a log to both sides, I was able to use these log properties, which say, hey, you can move an exponent over in front of the log. Now, our ultimate goal is to solve for x, figure out what's that unknown variable. Looking at this equation right here, if I wanted to get the x all by itself on the left, what would you have to do to both sides of the equation? If x is being multiplied by a log 2, can I just divide by log 2 then? But I have to do that to both sides, right, to keep it balanced? So if I divide this by log 2, divide this by log 2, well then those will cancel out. And I'm left with x equals log of 12 divided by log of 2. Our goal was always to get an exponent by itself, right? We're trying to solve for these unknown exponents. And now I've got x all by itself on one side. On the right side, though, I've got a calculation, log of 12 divided by log of 2. Is that something I can type into my calculator? Log of 12 divided by log 2? Yeah, that's the common log, remember? We have a button for that. So go ahead and figure out what x is for this problem. You get it? Yes. Now, when you're typing in a log in your calculator, you'll notice when you press the log button, it always gives you an open parenthesis right away. So when I type in 12, it's crucial that you close the parenthesis. All right, you must do that, because then when I divide by log of 2, if I didn't have that parenthesis there, it would be the log of 12 divided by log of 2. Like, I'd do that calculation first. Gavin? For now, let's just do like a single decimal place, just to be close enough. Just round to the nearest tenth. Anyone else get about 3.6? Yeah? So you can say x is approximately 3.6. One thing I want you to be careful of is looking at that original fraction that we have over there, the log of 12 divided by the log of 2. It's important to note that this log of 12 is its own value. It's its own number. It's its own calculation. You have to figure out what that number is first before you divide. So what I don't want students to do, which it is kind of tempting to do, is when you see a 12 over a 2, what do you want to change that to right away? Or like you see a 12 over 2, did any of you think, oh, can I just divide that and make it a 6? So you're like, oh, isn't that the same as log 6? What do you think? Is that equal? No, it's not. Right? We don't have a property that states that. So you're not allowed to do that, because you have to figure out this whole calculation first. Log of 12, get that number, then divide by log of 2, get that number. That will not be the same as the log of 6. Very different calculation. So make sure you do keep it with each of those logs separate. The only way we can combine logs into a single log is if they're being added or subtracted. Those are the only ones we have properties for. A log plus another log, or a log minus another log. Now, you may have recognized that the 2 and the 12, hang on, before we go here, if you look back at this, we had log of 12 divided by log of 2. Check it out. Those were our two numbers that we started with, the 12 and the 2. And so there's a little shortcut we can use without having to take the log of both sides, move the exponents, divide over the log. here's essentially the quick way to do this. This is what you're going to think about whenever you want to type something into your calculator when it has a base that's not a 10 or an e. So you have log base some number of another number, and you want to type that into your calculator. This is called the change of base formula because you're changing the bases. So like that previous problem, we had log base 2 of 12. Our calculation ended up being the log of 12 divided by the log of 2. So see how the answer goes up top and the base stays in the basement. Okay, you're definitely going to want to remember that basement analogy now. The base stays in the basement. And so to calculate that log base 2 of 12, or log of any base, you rewrite it as a division, as a quotient of 2 logs. But just like I was mentioning at the end of that last slide, make sure you calculate each log separately. Close those parentheses, then divide it. So log base y of x is the same thing as log of x divided by log of y. Definitely box this formula up, star it, do whatever you need. That's going to be essential for the rest of this unit, because we're going to be working with real applications when we want to solve for an unknown exponent in different scenarios. And we're going to need to type that into our calculator, and it's not always going to be a base 10 or a base e. All right, let's have you try using this change of base formula now. So log base 3 of 15. Go ahead and type that into your calculator. See what you get. But remember, there is no base 3 button on your calculator, so what do you have to do? This is your first run it using this change of base formula. Because those directions say evaluate the log, that means figure out, hey, what would that exponent have to be? We don't need to rewrite this in exponential form now. 3 to some power equals 15. I have no idea what that is. Something between 2 and 3. I don't know what that decimal is. So it's already in log form. Just use the change of base. So this is log of 15 divided by the log of 3. Again, make sure the base is in the basement. If you flip it, you're going to get a very different number. All right? Someone tell me what you get. 2.5? Anyone else 2.5? Yeah? About 2.5. Awesome. Questions yet? All right. So here's a problem, an exponential equation. 4 to the x equals 20. Now I can't rewrite 4 and 20 with a common base, like 2 to some power. So we have to use a logarithm. So what I want you to do first is rewrite this as a logarithm. Right? Rewrite it in log form because we're solving for that unknown exponent. Once it's in log form, evaluate that log. And you're going to have to use that change of base formula. Thanks. Were you able to type that in the calculator? Figure out how to use it? Cool. Does anyone have any calculator questions right now? I know there's a bunch of different types of calculators that I see out. Does anyone need a hand just figuring out, hey, how do I type this in? So you do 15 log divided by 3 log equals. So when you did what's probably going on is when you type log of 3, this is just showing you what the log of 3 was. Then you had to hit enter one more time for it to take that division into account. So see if you can type that in right now. Did you get it, Jaden? Nice. There you go. Cool. Other calculators?
Don't know if this should be allowed.
Yeah, Casio's allow you to type in the base. Yeah, that's fine. Shh, don't tell anyone. Anyone else? You figured out on your calculator how to do that? Type it in. You guys, everyone's good over here? Anyone else calculator questions? All right, so for this one, log base 4 of 20 equals x. And so to calculate a log base 4 of 20, we just need to rewrite that as the log of 20 divided by the log of 4. Type that in, and what do we get? 2.2, anyone? Yeah? Fantastic. About 2.2. So now you can solve for any exponent in any type of equation at this point. It's using this change of base formula. You got the calculator. Boop. It'll give you that decimal approximation. Hey, double check that. Did anyone ever do that yet? Go ahead and in your calculator, type 4 to the 2.2. Let's see if this actually does work. Now, it won't be exact, right, because we rounded off our final answer, but does it get pretty close to 20? Okay, 21.1. If you wanted it to be more exact, what would I have to do? Yeah, if you just add more, digits after that decimal, the more you have, the closer it will actually be to equaling 20 whenever you type that in for that exponent. All right, but for now, close enough is good enough. All right, here's the type of equation you can actually expect on your test, right? I'm not going to give it to you too easy. Got to give you a little bit of a challenge. So here is a regular old equation, 16 raised to the x minus 7th minus 5 equals 2. And you need to solve this equation for x. Let's just guess and check a couple thousand times. So solve it for x. Let me see what you can do. You're like a rock star. Is this stuff too easy for you? Should I make it more difficult? It's just the right level of difficulty. So can you calculate that? Oh, thanks. I'm seeing a few different answers though. I know. Oh, well, that's reassuring. Okay. Yep. Yep. Do that first. Yeah, and then you'd have to add 7 to that answer, right? Because that equals x minus 7. To get the x by itself, you still have to add 7. Yeah. You'd do the log division first, and then add 7 to whatever you get, which would be this. Yeah, and that's the right answer. You got it. Yeah, just check with him every time. His calculator lets you type in different bases. All right, I'm seeing people finishing up, so let's go through this. Before we rewrite it in exponential form, in logarithmic form, we need to make sure that we only have a base, an exponent, and an answer. So this minus 5 has to go, right? That's not part of our general exponential equation to log equation formula. So I've got to get rid of that 5 by just adding it. So we have 16 to the x minus 7 equals 7. Now I just have a base, an exponent, and an answer. So now we can go ahead and rewrite that in log form. So we'd say the log base 16 of 7 equals the exponent. And the exponent is x minus 7. Now we're solving for x, so I still need to get rid of that negative 7 on the right by adding 7. So this would be log base 16 of 7. Make sure you close the parentheses first, right? That logarithm is its own separate value. You'd have to keep that separate, calculate that first, and then you can add 7 afterwards to get the x all by itself. Now just type that into your calculator. But we can't type in log base 16 of 7. So we have to use this change of base formula. What I'm going to type in is log of 7 divided by log of 16. Remember that the base goes in the basement. Plus 7, and that will equal x. So typing this in, just have to be very careful with your parentheses. So we have log of 7, close the parentheses, divided by log of 16, close the parentheses, plus 7. See how that 7 is getting added after all the log calculations are done? Equals about 7.7. Yep. Anyone else? 7.7? So x is approximately 7.7. By the way, the little squiggly equal sign I've been using means approximately equal to. If you use a regular equal sign, I'm not going to knock off points or anything like that. But just know that x isn't exactly 7.7, but it's really close to 7.7. All right, now here's the trickiest problem. Not tricky, longer problem. So this is going to take a little bit more work because there's a variable up in both exponents. And when we solve an equation, we have to group the variables together, right? You got to combine like terms, put them on one side. Let's go ahead and jot this down. Five to the 5x minus 2 equals 2 to the 2x plus 1. And so the variables on both sides are up in that exponent position. You need to get it out of that spot. So we're going to do something that we did earlier today, where you take the log of both sides. So if I take the log of the left, I have to also take the log of the right. And so this is going to look like log of 5 to the 5x minus 2 equals log of 2 to the 2x plus 1. So simply taking the log of both sides. It looks weird with those big parentheses in there. You can keep them in there, but. So we're allowed to do that, performing the same operation on both sides of an equation. And now because we've done that, we've made both sides logs, we can now apply our log properties. That power property of logarithms allows us to move the exponent into the coefficient spot. So I'm going to take this whole exponent and move it in front of this log. Then I'm going to take that other exponent and move it in front of its own log. Now, since there's more than one term in that exponent spot, make sure you keep it in parentheses. We're going to have to do some distributing. So when we rewrite this, we're going to have 5x minus 2 times the log of 5 equals other exponent 2x plus 1 times the log of 2. Now our goal is to get the x's together, combine them. Right now they're in little parentheses. And if you look at those parentheses, like on the left, you see that you've got this log 5 outside the parentheses. Normally to get rid of parentheses, you'd have to distribute something into those parentheses. You could keep this as a log right now, but that's going to be kind of messy. Instead, can I actually figure out what log of 5 is? Isn't that just a number, some decimal? Go ahead, take your calculator, and let's just type in log of 5. Let's see, what is that number? What'd you get? What's log of 5? 0.7? Like 0.7 approximately? All right, so 0.7 equals, okay, 2x plus 1. What is the log of 2? What'd you get? 0.3? Okay, 0.3. Right, log 5, that's just a number. Log 2, that's just a number. So let's get that number instead. Now, what would be our next step for solving this equation? Yeah, let's just distribute. This just looks like a regular like algebra 1 problem at this point. Distribute, combine like terms, solve for x. You're going to have some decimals. That is okay. We are going to get a decimal for the final answer anyways. So when you distribute, you should get these decimals. 3.5x minus 1.4 equals 0.6x plus 0.3. So I'm going to group the terms with x. This is on one side and the constants over to the other. So when I subtract 0.6x from the left, we get 2.9x. On the right side, when we add a 1.4 to a 0.3, we get 1.7. At this point, just divide by whatever's in front of the x. And x is approximately 0.6. Anyone else get that? Close, some close to 0.6. All right, that's as difficult as it's going to get. And I don't think it's too crazy, right? Doesn't some of this kind of make sense? Some regular algebra. Just the one new thing is using those logarithms, taking the log of both sides so that you can move the exponent out in front, then just distribute, and it's like a regular algebra problem. Should we check our answers, do you think? Or should we just move on? I don't know. I think we should check. What if it doesn't work? 5 to the 5 times 0.6 minus 2 is 5. 2 to the 2 times 0.6 plus 1 is 4.59. That's close enough. We rounded a lot during that problem. Okay, any questions on this? Because you might have to do one on your own on the next slide. Any steps you want to go over? I know it's a longer problem, but it's not a difficult problem, right? Each individual step isn't crazy difficult. There's just a whole bunch of simple steps. So let's see you solve this one on your own. Nice. Yeah. Connor, good work. That's right. Okay. Oh, yes. Yes, good job. Oh, up here. Yeah, I was looking down there. I'm like, what did he do? Where'd he get those numbers from? Okay. Seen a lot of students finishing up. If you didn't, that's fine. Anyone get 4.7? All right, fantastic. If anyone wants to go through this with me a little bit later, let me know. We'll maybe have some work time at the end, and I'll go through it. But since it's a ton of steps, I want to move on to show you some new stuff. Whew. That's it. That's solving advanced exponential equations. And again, that's as difficult as it's going to get. Now, I think we're ready to finally learn what in the world are these used for. Dun 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 dun! Hey everyone, guess what? I have notes printed out for you for this part. Is that okay? So we're getting to the application piece. When would we actually use these logarithms? And so I've mentioned before exponential growth and decay, like at the beginning when we started graphing. And so we are going to actually look at how do we use this? How do we actually calculate something with an exponential growth or an exponential decay? So we're doing a bunch of word problems. So that's why I printed these out for you. So you don't have to, copy down these paragraphs or short novels that I have for a single word problem. Nah, it's not that bad. There you go. You are welcome. So you can still take notes in your notebook. I just wanted to give these to you so that you have those word problem examples. I didn't want you worrying about scrambling to write those down. So exponential growth or exponential decay. Growth means something's getting bigger. Decay means it's getting smaller and smaller. And so our general exponential format is going to look just like this. Y equals AB to the X. This is a simple formula. We're going to look at some more advanced ones on Tuesday. And each of those four pieces has a certain property that we're going to use when we apply it to some real world scenarios. The equation, like y equals that y, that's like your final amount. Hey, what am I going to get after so many years? What will the answer be? How much money will I have in my bank account or whatever? A is in the starting amount. Hey, I'm starting with this piece right here. It's important to note that the A is a coefficient of the base, right? The base B, that's the only part being raised to the exponent. A is not being raised to that power. B is what we call the growth factor or the decay factor. Based on this number that we'll be raising to different exponents, if it's bigger than 1, it's going to be growing. If that number is less than 1, like a fraction, it's going to be decay. Things are going to get smaller every cycle, every iteration. Then X is just the time that passes, right? If I say, hey, if I get this much every year, how much will I have in 10 years? You plug a 10 in for X then. So it's a pretty straightforward formula. So let's try using it. A population of 84 rabbits doubles every 3 years. So how many rabbits will there be after 15 years? So here's our general formula. Y equals A times B to the X. And we basically need to identify each of the values here and figure out what's it asking me. So when I read, how many rabbits will there be after 15 years? It's asking for like a final amount. Hey, after 15 years goes by, what are we going to have? What's that final number going to be? So we're solving for y, so it's nice and straightforward. Y equals A is the starting amount. How many bunnies are we starting with? Population of 84 rabbits, so 84 is A. B is the growth rate or the decay rate. So first off, is the population of rabbits, is it growing every 3 years or is it decreasing every 3 years? It's getting bigger. How much is it growing by? What's the word problem say? Doubling. So what number do you think we should use for doubling? 2, right? Times 2 means to double. So it's 84. And I'm going to put B in parentheses because only that base is going to be raised to the exponent. 2 to the x. Now, x you have to think about just a little bit. X is the number of time intervals. So we want to know how many will there be after 15 years. Should I put a 15 in for that exponent, though? Seems like we should, right? It's after 15 years. But how often does the population actually double? Only every 3 years. So in the span of 15 years, how many times will the population actually double? Only 5 times, right? You just divide those. So if that ever happens, or like the numbers don't match up, you write the number or the time that passes divided by however often that change occurs. And you can just think about that, every 3 years and 15 years, that's going to happen 5 times. So you're just kind of just doing a little division problem right there. So you can say, well, this doubling, this 2, is only happening 5 times in that 15-year period. So you don't always put just the year there or whatever. You have to think a little bit about it. How many times will that occur? So we can easily find the population of rabbits just by taking 84 times 2 to the 5th. Well, let's grab our calculators. So we said 84 to the 5th, you write the base, and then for an exponent, you use this caret key right here. It's called a caret, 100%. That's the caret. And then it should give you a little exponent. Some calculators, it might show the actual caret there, and that's going to the 5th power. Hit enter, and anyone else get 2,688. 2688. And that's an exact value, so I can use an equal sign. 2,688. It's a word problem, so we need our units. That's rabbits. Wascally wabbits. Is that a lot of bunnies?
Yeah.
Oh my gosh, yeah. That's crazy. Here's a science application. Yes, I love science. A sample of 256 milligrams of uranium has a half-life of 10 years. How much uranium will remain after 60 years? So a common property of radioactive substances is that they decay over time, meaning they become less radioactive, they become smaller, they lose their mass because that radioactivity kind of messes with them. And so it's really interesting because the more massive this radioactive material is, the more of it will decay in a certain amount of time. But if there's less of it, it takes longer for it to decay. This property is called its half-life. So the half-life of a material simply means how long it takes for there to be half of that stuff left over. So let's use our formula. Y equals A times B to the X. And again, this question is still asking how much will be left over after 60 years. That's Y, right? It's asking for the final amount. 60 years from now, what will we have? So we're solving for Y equals A is the starting amount. How much uranium do we have at the beginning? 256. Now for the base. When the bunnies were doubling, we put in a 2 because that's what double means, times 2. What number do you think we should use for a half-life? 1/2, right? It's going to be cut in half every one of those time cycles. So if you ever see half-life, you put 1/2 in the parentheses for the base. This is the decay factor, we call it. And then our exponent. What says after 60 years? Should I put 60 in for that exponent? No, because its half-life is every 10 years, meaning it's only going to get cut in half every 10 years. So think about over the course of 60 years, how many times will it actually cut in half? 6 of them, right? Because that 10-year interval is going to happen 6 times. So we'd put 6 in for that exponent. It's just only going to get cut in half 6 times over that 60-year time frame. And again, we calculated that just by 60 divided by 10. So 256 times 1/2 to the 6th power. Take your calculator out. Let's see what we get. 256 times, for 1/2, I can do a fraction or just type 0.5 raised to the 6th power. You get a 4. Anybody else get 4? Wonderful. Oh, that's awesome. 4, units? Yes. That's right. Y equals 4 milligrams. Got to keep those units in there. And that unit has a G, so it's a G unit. Now, these scenarios, the growth factor or the decay factor was pretty straightforward. It was given to us. It says doubling or cut in half pretty much. Normally, with these exponential growth and decay problems, you're going to be given a percentage, like it's growing by 3% every year. And you wouldn't put in a 3 because that would be tripling. And getting 3% of something is much, much smaller. So typically what you're going to see for an exponential growth or exponential decay problem is we're going to have to calculate what is that growth factor or that decay factor. Here's how you calculate this. You start by taking that rate, and the rate is going to be given as a percentage. So you take that percentage and you convert it to a decimal. Everyone know how to convert a percent to a decimal pretty easily? You just divide by 100, and it moves the decimal over 2 places. 2 places to the left. So for example, 15%, if you just divide 15 by 100, you'd get 0.15. Okay, so you move the decimal over 2 places. This gets tricky if you have single digits. So if I have 2%, that's not 0.2. That would actually be 0.02. So you have to divide by 100, move it over 2 times. Sometimes students will just put 0.2, and that's actually 20%, which is way bigger than 2%. So just be careful with those single-digit percentages. So you get the decimal, and then these formulas are almost identical, right? What's the only difference between the two of them? One's a plus, one's a minus, and that's also pretty straightforward, right? The growth uses addition because growing means getting bigger. The decay means you subtract it because subtraction is taking away, making smaller. They both start with 1, so it's either 1 plus that rate or 1 minus that rate as a decimal. And so if you think about that, this is going to be a number greater than 1, like 1.15 or 1.02, meaning you're getting a little bit more every time. For decay, if you subtract that from 1, you're going to get like 0.85 or 0.98. That means you're getting a little bit less than you had before each time. It's getting smaller and smaller. So let's try applying these. The value of a comic book collection has been growing by 50% every year. By the way, this is not my own comic book collection. Mine is not worth this much. Sad face. If it's currently worth $30,400, what was it worth 10 years ago? So this one's a little bit different for a couple reasons. First, we've got a percentage that we have to take into account. So we're going to use one of those new growth or decay formulas. But also, it's a little bit backwards because it says that it's worth 30,400 today. What was it worth at the beginning, way back when? So in this case, instead of starting with A and solving for Y, we're now actually given the Y value. So this is Y. And we want to know what was it worth 10 years ago. That's A. It's asking what was the starting amount? What was it when we began 10 years ago? Oops. So Y equals, let's just write the general formula. A parentheses 1. Am I going to do 1 plus or 1 minus for this scenario? Is that a, yeah, so is the value growing or decaying? So from the start, it was growing, right? It was getting more and more valuable as time went on. So that's growth. Because we don't know what it started out as, but I do have the final amount. So it's going to be 1 plus the rate raised to the x, or raised to the t for time. I'll keep that as x for you. So y is the current value. That's the ending amount. We know that it ended up being worth this much. I don't know what the starting value was. How much did this guy pay for his collection 10 years ago when he started? So in this case, the starting amount is A. I don't know what this started as. Parentheses, 1 plus, because the value grew from whatever he bought it for, that cheaper price, it grew over time, and it got to the point where it's now worth 30,000. 1 plus R. What number do I use for R? Should I use 50 because it's 50%? So that rate would equal 0.5. You convert the 50% to a decimal. So it's 1 plus 0.5. And what number do I use for my exponent, do you think? It says 10, but how often does it grow by 50%? Every year. So yeah, in 10 years, that would happen 10 times. So 10. All right, so we've got our equation, and we're solving for the variable. We're solving for A. And look at this. A is being multiplied by the base to the x. So how can I cancel that out? You can't distribute because of the exponent. PEMDAS says exponents come first. But if I just want to get that A by itself, how do I get rid of this thing on the right? What operation would I do? Just division, right? I can just divide. Whoa, what's that? By 1. Hey, what is 1 plus 0.5? Is it okay if we just add that together right now? 1 plus 0.5? 1.5 to the 10th. Over here, you divide by 1.5 to the 10th. So if we did that, this cancels with that, and you're left with just A, the starting amount. All right, so that's what we're going to actually type into our calculator. 30,400 divided by 1.5 to the 10th. And that'll give us A, the starting value of that collection. So 30,400 divided by 1.5 to the 10th. Should look just like this. Anyone else get about 527? 0.18. We're talking about money and dollars, so I'll take 2 decimals for cents. 527.18. $527.18. So this guy bought all these comics for 500 bucks. 10 years later, it's worth over 30,000. Whew. It's a nice investment. What's that? A little bit. A little bit. Okay, I've got one more problem and we're done. Any questions on this before we move on, though? We were just solving for a different variable this time. Basic rules of algebra still apply. I know what you're all thinking. But wait, Mr. Wojcik, we haven't used logarithms yet with these word problems. Please, can you give us a problem where we have to use a logarithm? All right, fine. You've just inherited a car. Hooray! It's currently valued at $2,400. The car was originally purchased for $32,000 and it's been depreciating by 18% every year. How old is the car? Is this growth or decay? Okay, you buy the car for a lot of money. As you use it, the value goes down, right? That's what depreciating means. So this is going to be exponential decay. So we're going to use the y equals a times 1 minus r to the x, right? Decay, we use subtraction. We subtract the rate from 1. Let's plug in our numbers. Y is the final amount. What's the final value of this car? Like, what's the value right now, today, at the end of the time period? Okay, that's the lower number, right? It depreciated. Now it's only worth $2,400. But what was the starting amount? How much was this car when we first bought it? That was $32,000. Parentheses, 1 minus the rate. Now this 18% is going to be what decimal? 0.18. Let's move the decimal over 2 spots to the left. So 1 minus 0.18 to the x. Wants to know how old is the car. That's the time. We don't know what the time is. Well, that's in the exponent spot, so I guess we get to use logarithms to solve for an unknown exponent. So we want this equation to have just a base and an exponent equaling an answer. So what do I have to cancel out first on both sides? Is everything on the right side being raised to that exponent? No. What's not being raised to that exponent? That starting amount, A, that's just being multiplied right here. So let's just divide that out just to get rid of that. Divide by the 32,000. All right, so dividing that off gives us 0.075 equals, no, over on the right side, I can do that 1 minus 0.18 also. That's going to be 0.82 to the x. So looking at that equation in purple right there, that's a basic exponential equation. That's just like the first problems we did with logs today, right? I have an answer, a base, and an exponent. We want to solve for that unknown exponent. So you can forget about the cars and everything like that, starting amount, final amounts. Just solve this for x. We're going to rewrite this in log form. So we'd say log base 0.82 of the answer of 0.075 equals x. Now I don't have a log of 0.82 in my calculator. We can just use that change of base formula where you write the division of two logs. So we'd say the log of 0.075 divided by the log of 0.82. Log 0.075, close parentheses, divided by log of 0.82. And we get approximately 13 years old. Anyone else get 13? Wonderful. All right, who has questions? Clarifications? Or any steps you want me to go over? Feeling okay with this? Excellent. Well, good job.